to record this session so everyone can see my screen. This is the review for the Chem 112 practice exam number 1, which covers chapters 1 and 2. Starting off with a relatively straightforward exam just to make sure everyone has their fundamentals down for the later parts of this course. Is everyone able to find this exam on Canvas? Is everyone able to find this exam on Canvas? Is everyone able to find this is practice exam number 1? So let's get started. We're looking at question 1. We have to show all major resonance forms. Okay, so to do that, we're going to show step by step using arrow pushing notation how we can distribute electron density throughout this molecule. So the first electron pushing scheme, we're going to kick our electron density up and generate a carbon-centered anion. Okay. Next, of course, we can kick our electron density in to our ketone system and generate another enolate-like motif. Make sure you're noting your formal charges appropriately when you're drawing your resonance structures, and make sure that you are paying attention to make sure that you're following the octet rule. Continuing on, we can't explicitly delocalize via resonance into this adjacent double bond. It's conjugated, but we can't really showcase that with arrow pushing notation. We can, however, kick our electron density up to this second alpha position, almost like this is almost like a more explicitly drawn version of an enamine. I guess you can think of it that way. And as you'd expect, enamines have very similar reactivity patterns to your typical Okay, so here's our next resonance structure. We can then kick down our electron density and generate the following resonance structure. Remember, you use double-headed arrows for resonance structures. And remember, your major resonance structures obey the octet rule in most cases, barring cases involving sulfur, which aren't particularly common. Okay, so now that we have all of our major resonance structures, does this make sense so far? The process of arrow pushing notation. You can kick your electrons down into a pi system and break a pi bond to generate a lone pair. We've repeated that process multiple times to generate a total of 5 unique resonance structures. Does that make sense? And really don't be shy to ask questions during this session. I, of course, know how to solve these problems, but if there are any parts that you need clarifying, this is what this session is designed for. So continuing on now, we have these structures, so let's try to answer some questions. So we used arrow pushing notation, so we checked that box. Place a box around the resonance structures that are largest contributing structures. Okay, so first off, what does everyone think? So we have A, B, C, D, and E. Which structures would you consider major? Which structures would you consider major? Which structures Obey the octet rule and place negative charges on the most electronegative atoms. Which structures are major? Which structures are major? D, yep, D is a perfectly reasonable major structure because it has a negative formal charge on oxygen, and A, exactly right. So D and A would be our major structures. Not one of these structures is preferred over the other, so they're both equally preferred. I can't think of any particular reason why one structure would be substantially preferred over the other. In both cases, we place a negative formal charge on the most electronegative atom. We avoid a carbon or nitrogen-centered anion, and as a result, these structures would have the greatest contribution and probably most accurately describe the resonance hybrid under these current conditions. Okay, so we've answered the first question. So we've indicated the largest contributing structures. Now we have to label all carbons that have a partial negative charge and all nucleophilic carbons, which are essentially carbons with a large amount of electron density. Okay, so let's do just that. So let's draw out our structure and let's label our nucleophilic carbons. And let's really focus on those that are substantially nucleophilic by looking at carbons with a large amount of electron density as indicated by the major resonance structures. So if we look in our resonance structures, if we look in all of our different resonance structures, we see that first and foremost, we're going to label all of our carbons where we have a negative formal charge. So in this case, we'd label this carbon here and this carbon here as nucleophilic carbons, because in our resonance structures, they explicitly have a reasonable contributing structure with a large amount of electron density located on that carbon. As you remember from our class discussion, carbons that are alpha to a carbonyl are typically nucleophilic in many cases. So these are our two nucleophilic carbons. As in our resonance structures, there are contributing structures with a substantial amount of electron density on those carbons. Does that make sense to everyone? Does that idea make sense for labeling our nucleophilic carbons? Any questions on this example? So nucleophilic carbons are carbons that are electron rich. We look at our resonance structures and we look at each of our contributing structures and we identify the carbons with a large amount of electron density. In this case, in structure B, this alpha carbon has a substantial amount of electron density because it has a localized lone pair in one of the contributing resonance structures. Likewise, in structure C, there's a large amount of electron density on the indicated alpha carbon to this imine functionality because there is a localized lone pair and a partial negative charge on this alpha carbon. Because we have these two carbons in our contributing structures as having a large amount of electron density, those carbons in our resonance hybrid will be relatively electron rich and will be considered nucleophilic. These carbons will have a large amount of electron density relative to other carbons in our molecule. Does that make sense? Perfect, perfect. Okay, so this problem overall wasn't too bad. It's based on the homework. So if you've worked on the homework, it should look pretty similar. Any other questions before we move on from this example? So, in this next question, we're asked to circle and name each functional group in the following molecule. Okay? So, we have an aryl group. We have an alcohol. We have an ether. We have an alkene. We have an amide. Oh, let me circle the more appropriate amide right here. Let's look at some other functional groups from our list. Let's look at some of the other functional groups from our list.
What makes this amide more appropriate than the other?
Because this amide, this isn't quite an amide. It's a different functional group that we're not going to focus on a ton, at least in this session. It's a variant of an anhydride functional group. So the reason why I circled this as our amide is it matches our traditional amide a little bit more appropriately. We also have an amine functionality and an imine functionality. So there are a range of functional groups. I'm mainly looking for the ones that we covered in the table in our note set, as there are a few other functional groups that will be covered in organic too, and when we get towards the NMR and IR spectra analysis. So these are all the major functional groups found in this molecule. Any questions on this? Most of these functional groups are from our table in the chapter 1 notes. Any questions on that?
Is that top oxygen in the leftmost ring system, is that a part of any functional group?
It can be considered as part of an amide. It can be considered as somewhat part of an amide. This entire functional group here, I didn't cover it in the chapter 1 notes, so I'm not expecting you to know this. This is an imide functional group, which is of the form like so. So it's technically part of the imide functional group.
Okay.
Mm-hmm. In the example that you receive on the exam, the functional groups will be a lot more clear cut. Because this example was designed as a practice exam example where you have a little bit more time and we'd have a lot more time to review, I tried to include some of the more odd functional groups, or try to include these functional groups in the context of a more complicated molecule. If you're able to correctly identify all of the functional groups on the right-hand side of the molecule and the amide functional group, you'd be all set for the exam. Any questions on this example? Any questions on the first part in this example? Okay, so let's keep going now. We're asked to label all sp2 and sp hybridized atoms. So this is also accounting for resonance effects. So I'm going to label all my sp2 hybridized atoms with a purple star. So by resonance, each of these imide or amide nitrogens have a substantial amount of sp2 character due to contributions via resonance. So all of these conjugated atoms which are participating in resonance have an sp2 hybridization. Likewise, looking at this amine nitrogen, this amine nitrogen lone pair is conjugated with the pi system, and in turn, it adopts an sp2 hybridization. So we have a large amount of conjugation present in this molecule. Likewise, what would the hybridization be for these two oxygen atoms? What would the hybridization be for these two oxygen atoms?
sp3.
So as these oxygen lone pairs are potentially conjugated to this larger pi system, would the lone pairs prefer to be present in an sp3 orbital or present in a p orbital so they can participate in conjugation and be delocalized throughout this pi system?
P orbital.
Yep, so each of these oxygens are sp2-like in terms of character. They're flat rather than having a three-dimensional or bent character. Does that make sense?
Yep.
Just like what we saw with the ester oxygens and with our conjugated. Yes, that is true from the traditional sense, but keep in mind that resonance contributions and conjugation influences the hybridization and shape of atoms participating in resonance and conjugation.
Yeah, don't those override it? Those
Yes.
traditional rules?
Yes. And so the lone pairs would prefer to occupy a p orbital so they can participate in conjugation and delocalization. So now that we have all of our sp2 hybridized atoms labeled, we're asked to identify how many sp2 hybridized atoms do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21. You could also say 19 if you say if you say explicitly that you're saying that this ketone oxygen is not hybridized. And that would be a reasonable interpretation. And depending on how you phrase it, you can either view these oxygens as sp2 hybridized, or you can view them as unhybridized and just using their p orbitals for bonding. Both interpretations are reasonable for these ketone oxygens. I find it's easier just to treat them like they're sp2-like. Does that make sense to everyone?
Is a ketone a subfunctional group then?
A ketone is its own unique functional group, but it is a component of functional groups such as amides, etc. They're sort of derivatives of ketone functional groups.
But we wouldn't need to include it if we see one.
No, because it's not a ketone, it's more accurately described as an imide or an amide. Does that make sense?
Yeah, that clarifies. Thank you.
Yeah, because if it was just a carbon-carbon, then there's no.
If it was something like this, then it would be best described as a ketone.
Okay.
You want to use the most accurate functional group label that you can for each of your functional groups. Does that make sense?
Yep.
Perfect. And just to make sure, for students who are joining, are there any students that are trying to join this meeting that are sitting in the main room? I'm just gonna send out some invites once again, just so that way I make sure that I think I got everyone.
Yeah, I joined late, and you sent me that right away. So
Okay.
thank you.
So let's keep going now, and let's look at the next question in this sequence. We're asked to label the most basic atom. So we're looking for the most basic atom. What are we looking for here? In terms of our criteria, we want a localized lone pair. And in turn, we want a relatively high energy lone pair. So, looking at each of the atoms found in our molecule, in this molecule, which atom has the most basic lone pair? Which atom has the most localized lone pair? Does anyone have a proposal so far?
Bottom left oxygen in that little arrow structure.
The bottom.
No, sorry, not the arrow structure. The one you're, yeah, that one.
Okay. So let's list our candidates. Let's list our candidates down here. So we have some options to discuss. So let's draw out and let's observe and let's try to identify the most basic lone pair in the following molecule. And in general, we want a localized lone pair. That is relatively high in energy. So redrawing our molecule. So we have one proposal that this bottom oxygen is the most basic.
Can I change my proposal?
Yes.
I don't like that oxygen anymore. I like that
Okay.
nitrogen in the middle.
Okay. But to explain to help elaborate why you changed your proposal, if we think about the pKa of our conjugate acid, the protonated ketone has a pKa of around -1.7. So,
Yeah,
yep, that's perfectly reasonable.
I forgot that we were trying to get the basic atom.
So then if we're aiming for the most basic atom, you're thinking now this nitrogen? Was that your proposal?
It was either that nitrogen or the nitrogen one more above the one you're currently on. That one, yeah.
This one. Okay.
No.
So let's talk a little bit about this. So if we entertain the option of this nitrogen, my question to you is this nitrogen lone pair localized or delocalized? Yep. There's one more line for the. So entertaining the option of this nitrogen, is this lone pair localized or delocalized? Is the lone pair localized or delocalized? What does everyone think for this nitrogen lone pair? It's delocalized. And so if we think about the conjugate pKa, so if we think about the conjugate acid pKa of an amide, what is the approximate pKa of a protonated amide? What is the approximate pKa of a protonated amide? Taking out our pKa tables, what is the approximate pKa of a protonated amide? looking through your pKa table, what do we think?
About 9 to 11.
That would be a protonated amine.
Oh, damn it.
That's one that we should write down though. The pKa of a protonated amine is between 9 to 11. So rather than directly find so thinking about the pKa, keeping in mind that this lone pair is delocalized, we can at very least assume that the pKa is going to be less than 9 to 11, right? Because by definition, an amine, which is of the form RNH2, has a localized lone pair, and in turn, a more basic lone pair. Right? So because if we were to deprotonate this protonated amide, we generate a very stable conjugate base. We know at the bare minimum our pKa is going to be less than 9 to 11. Interestingly enough, just to show you, we have a qualitative argument. We can also argue via comparison. Amides are typically actually protonated at the oxygen. And the pKa of this protonated amide, amides are actually relatively acidic compared to amines. So likely these two amide nitrogens are not going to be very basic because our lone pairs are delocalized, and as a result, if they pick up a proton, will generate a relatively acidic species. These lone pairs are quite stable in this current form. Does that argument make sense to everyone? For those who are curious, a protonated amide has a pKa of negative 0.4 if you're looking at a more quantitative table. So amides are not very basic at all. Does that argument make sense, both from a quantitative and qualitative perspective? Delocalized lone pairs are not very basic because the conjugate acid is going to be quite acidic, because if you remove a proton, you can generate a very stable conjugate base. Does that argument make sense to everyone? Okay, so now we're going down the list. Does anyone have another proposal? So we said these three candidates, they're reasonable first guesses, but when we think about it a little bit, they're likely not going to be very basic. So what's the next thing we should look at? What's the next basic functional group present in our molecule? So we're looking for a localized lone pair and a high energy lone pair. So then, what's the next lone pair that we want to look at? What does everyone think? Which amine? So we have amine A and amine B. Which amine would be the most basic? Okay, so we have a proposal for B. Okay, so now we're doing a head-to-head comparison between what I would consider almost an allylic amine and I guess I would consider an imine. So my question to you is, looking at these structures, which of these two lone pairs, A or B, is localized? Which of these two lone pairs, A or B, is localized? Which lone pair is localized and most centered on nitrogen? And let me just remember to draw the methyl group just to complete thing. Which of the lone pairs is most localized? A or B? B, yep, that's exactly right. Because if we think about the orbital that the lone pair is stuck in, this lone pair is stuck in an sp2 orbital. So we have a localized and basic lone pair. While lone pair in structure A, and this is what's really cool, can be kicked down and delocalized via resonance into nitrogen B. Does that make sense? So we have two effects at play here. First, we have just an atom effect where the lone pair on our bottom nitrogen B is more localized, less stabilized via resonance, and as a consequence, it's generally going to be more basic. And we have a substantial resonance effect at play where we can look at a minor resonance structure where a large amount of our electron density is placed on our bottom nitrogen. So we have both a resonance effect and an atom effect, which in turn means that this bottom nitrogen would be our most basic nitrogen. Does that argument make sense to everyone? Does that argument make sense? It's the most localized lone pair, and there's donation of electron density into nitrogen B via resonance. Does everyone see that? Any questions on this idea? Now you may ask, why is this important? Well, if you try to engage these types of cyclic systems in reaction with electrophilic reagents, nitrogen B often can preferentially react depending on your choice of reaction conditions. So identifying the most basic lone pair in turn is very useful to noticing and noting localization of electron density and helping to understand patterns in reactivity. Does this example make sense? Any questions on this example? So as you can see, even if you encounter a functional group that you've never seen before, you can utilize both quantitative and qualitative arguments to rank different functionalities in terms of acid strength and base strength. So you don't always need to have a detailed pKa table to draw reasonable conclusions. Any other questions on this before we move on? Okay, so let's keep going now and let's rank the following molecules in order of acidity or basicity. In this case, we're asked to rank the following molecules in order of increasing basicity. So, keeping in mind and looking at each of our lone pairs, the main difference in these three molecules is the hybridization of our central atom. So we have an sp2, an sp3, and an sp central atom. In general, lone pairs on an sp atom are more stable, and as a result, our lone pairs are less basic. So, which lone pair would be the most basic lone pair? Which lone pair would be the most basic lone pair? So we
The
have
sp3.
A, B, and C. So the sp3 hybridized lone pair would be the most basic, followed by sp2, followed by sp. It's the exact same argument that we use to think about pKa values of our vinylic protons, right? The alkyne proton has a pKa of around 25, while our vinyl proton has a pKa of around 43. The more stable the base, the weaker the acid. The more stable the base, the stronger the acid. Does this argument make sense to everyone? Lone pairs on sp hybridized atoms are more stable than that on sp3 hybridized atoms in general. Because the lone pair is more stable, it's less basic. It's less likely to function as a base. The more stable your lone pair, in general, the weaker the base. Any questions on this example?
Nope, not for me.
Okay, so let's keep going now and let's look at each of these molecules and let's rank them in order of increasing acidity. So if we think about conjugation, let's look at each of our conjugate bases and let's assess how each of these conjugate bases are stabilized via resonance and conjugation effects. Okay, so looking at each of these structures, which of these structures is most stabilized via conjugation? Which of these structures has the greatest amount of atoms conjugated via resonance? Which of these atoms has the greatest amount of delocalization as a result of resonance? So in this case, we are able to delocalize our electron density over. So if we were to draw out we're able to delocalize our electron density over 5 conjugated atoms. While in the structure on the far right, we're able to delocalize our electron density over 9 atoms that are conjugated via resonance. Yep. So which structure would be the most acidic? Which structure has the most stable conjugate base? Structure on the right, yep, this will be our most acidic because it's most stabilized via resonance, followed by the structure on the left as it experiences some stabilization as a result of conjugation and resonance effects, and the structure in the middle is the least acidic. Does this example make sense to everyone? Does this idea make sense to everyone? So essentially, the more stable your conjugate base, the more acidic your parent acid will be. That's why, for example, benzoic acid has a pKa of around 4.2, while this acetic acid derivative will have a pKa of around 4.7. So there's a pretty minor but substantial difference in pKa as a result of resonance and conjugation effects. It's not as dramatic as in other examples that we'll see later on, but nonetheless, it's important to note. Does this make sense to everyone so far? The pKa on number 2. Let me look it up just for completeness sake. The acrylic acid pKa is around 4.4 roughly. Okay, let's look at another example. We're asked to rank the following molecules in order of increasing acidity. Make sure that you add the formal charges. So I'm going to put the formal charges in, and then we'll be ready to discuss this example. So, first and foremost, we need to consider atom effects. So, which of these structures are most acidic, noting atom effects? Which of these structures are most acidic, noting atom effects? So let's draw out each of our conjugate bases. So let's draw out each of our conjugate bases, and let's see what we can see from there. So the acid that generates the most stable conjugate base will in turn be the most acidic species. So we see a lot of interest on the sulfur containing molecules. The reason for that is because sulfur has a pretty dramatic atom effect and is quite effectively able to stabilize electron density on sulfur. Okay, so thinking about this in terms of pKa values, in terms of stable conjugate bases, we're just going to put a star next to each of our sulfur-containing conjugate bases. Okay. Now, looking at atom effects, we would expect the sulfur-containing conjugate bases to be the most stable, and in turn, the sulfur-containing protonated species to be the most acidic. One factor that we should consider is that the carboxylic acid derivative, we can delocalize our sulfur electron density and stabilize our parent acid via resonance. So our parent acid is stabilized via resonance. So then we'd expect our thioketone, when protonated, to be the most acidic species, as its conjugate base is stabilized via atom effects, and our parent acid is the least stable species because it's not, the parent acid is also not stabilized via resonance effects. Does that idea make sense to everyone? Does that concept make sense to everyone so far? Next, we have our sulfur-containing compound, because the sulfur-containing compound is able to very effectively stabilize our charge in our conjugate base, and in turn, our conjugate base as a result is relatively stable, which results in a more acidic parent acid. Okay, now we have to deal with our ketone series. So, just to give you some pKa values to inform your discussion, a protonated ketone has a pKa of around -7.2. A protonated carboxylic acid has a pKa of around -6.0, while a protonated amide has a pKa of around -0.4. So to help explain and to help us understand and to help us rationalize these pKa values, let's try to think through and let's try to focus on our parent acid and our conjugate bases for each of these compounds. So, first and foremost, if we think about our ketone, our parent acid is not particularly stabilized via resonance. Comparatively, our carboxylic acid and our amide, our parent acids are heavily stabilized via resonance contributions. And as a result, if we look at one of our amides contributing structures, we have a structure where we're able to partially stabilize our positive charge by placing it on a relatively less electronegative atom. So in turn, this amide, protonated amide, would be our most stable parent acid, and in turn, our weakest acid. So we put this at number 5 on the list. Looking at our carboxylic acid, our parent acid is able to be partially stabilized via resonance. So this would be our 4th most acidic species, while our ketone, our protonated ketone, would be our 2nd most acidic. So it's almost the inverse of the argument we use to rank our alpha protons in order of acidity. This time we're looking at how resonance effects can stabilize our parent acid and in turn affect the pKa of our parent acid. This is a somewhat difficult example, but does the reasoning that we use make sense for this example? You should at least be able to distinguish between the pKa values for these two compounds for sure. Does this argument make sense to everyone so far? Any questions on this example?
Are there two number twos?
Ah, sorry, this should be number 3. There we go. I was numbering from the bottom up and then from the top down, and I didn't make sure that the numbers matched. There we go. Yep, so in this case, we look both at our parent acid and our conjugate acid. In this case, if we look at each of these structures, our parent acids have varying degrees of stability based on atom effects and resonance effects. The amide is the least acidic because we're able to stabilize our positive charge and we're able to delocalize our positive charge onto a less electronegative atom. So we observe less charge effects and in turn a less acidic species for molecule number 5. Comparing number 1 and 3, it just comes down to atom effects. Sulfur is more effectively able to stabilize electron density and stabilize our conjugate base. While comparing number 1 and 2, number 2 is a less acidic species because we're able to delocalize and stabilize our parent acid slightly via resonance. And most importantly, our conjugate base is stabilized not only via resonance, but also via very strong atom effects. Does this make sense to everyone? So it's a combination of the parent acid stability differences and the conjugate acid stability differences. Any other questions on this example? Any other questions on this example? So let's keep going now. Let's try to rank the following molecules in order of increasing basicity. And in this example, we're looking at inductive effects. And the stronger our inductive effects, that in turn leads to a weaker base, as we have all of these different functionalities pulling electron density away from our basic atom. So then, which of these structures would be the most basic following that framework? Which of these structures would be the most basic? So if we have A, B, and C, which of these structures would be the most basic? A, B, or C?
It would be A because it only has 1 chlorine and thus a weak induction effect.
Yep, so this would be the most basic because it has the weakest inductive effect, exactly right, followed by B, followed by C. Does this example make sense to everyone? Okay, let's keep going now. This is where we have our classic alpha proton ranking. This is where we have our classic alpha proton ranking. So the pK of an ester is around 25. The pK of a nitro group is around 8 to 9. The pK of an acyl chloride is around 17. The pK of an aldehyde is around 20, and a pK of a nitrile is around 30. To understand these pKa values, rather than just memorizing these pKa values, let's look at each of our conjugate bases. Let's look at each of our conjugate bases. So, for our esters, this oxygen is functioning as a donor group. And this donor group, in turn, destabilizes our charge on adjacent atoms. And it minimizes the contribution from one of our other major resonance structures, where we kick down our lone pair into our ester and generate this enolate functionality. This oxygen is kicking electron density into our already electron-rich pi system, and this in turn destabilizes our negative charge. That explains why it's a little more difficult than usual to remove this proton. If we compare that to our nitro group, if we look at our conjugate base for our nitro group, in our nitro group, we have a lone pair that is heavily delocalized and stabilized via resonance. We have this lone pair that is delocalized and distributed over multiple electronegative atoms. That explains why the nitro group alpha protons are substantially more acidic. For the acyl chloride, would someone like to tell me what is the major effect at play for the acyl chloride? What effect do we have that's leading to a substantially more stable conjugate base than usual? What effect do we have? What do we call this effect?
Induction.
Yep, exactly right. So we have a strong inductive effect, which stabilizes our electron density on our anionic carbon and on adjacent atoms as it's delocalized through our pi system. Does that make sense to everyone? Because our conjugate base is stabilized via inductive effects, we have a substantially more acidic proton than usual. The aldehyde, we'll talk more about this later on in the class. It's a combination of hyperconjugation effects and just the lack of donation from adjacent atoms. This hydrogen is not a really effective inductive donor. So as a result, the main factor for an aldehyde is just that this anion is stabilized via resonance. And that explains why it's relatively easy to remove an aldehyde proton. Finally, if we look at the conjugate base for a nitrile, we end up with a nitrogen-centered anion, and this anion is not particularly stable. It has weaker atom effects than our other examples where we're delocalizing our electron density onto oxygen. And as a result, because our anion is less stabilized via resonance, it's harder to remove our proton and our acid is weaker. So we see a larger pKa value. So number one, our most acidic would be our nitro group, followed by our acyl chloride, followed by our aldehyde, followed by our ester, and finally our nitrile. This is a pretty nice example as it combines resonance and inductive effects quite nicely. Does this idea make sense to everyone? Is everyone comfortable with this example? This is pretty similar to what you'd see on the actual exam in terms of difficulty.
This is something that we can just look up the pKa for, given probably, I think only
Sure.
the
Sure.
middle one is the hardest one to look at the pKa for.
Sure, but you should understand the reasoning involved to get to each of these pKa values, because
Right,
you
right.
may see a structure that's a little bit different than that in one of the common pKa tables.
Okay.
Does that make sense?
Yeah.
Perfect. Any other questions on this example? So let's keep going now. So in this case, we are asked to draw the products of each acid-base reaction using arrow pushing notation. We're indicating the pKa value for each reactant and product and indicate whether the reactants or products are favored at equilibrium. So I know my ketone has a pKa of around 22. If I showcase my acid-base reaction using arrow pushing notations, where I break my atom hydrogen bond and form a new bond to that hydrogen atom, I generate as a product the following ketone anion and ethyl alcohol, which has a pKa of around 17. So which side of the reaction is favored, reactants or products? Is this reaction reactant favored or product favored? Is this reaction reactant favored or product favored?
Reactant?
Reactant favored? Yes, because
The
as we
stronger pKa is on the product side. Sorry.
yeah, exactly right. The product is more acidic, and as a result, this reaction is reactant favored. Exactly right. Does this make sense to everyone? Does the reaction mechanism drawn make sense to everyone?
And that's because the product is more acidic, so that's why it's reactant favored, you were saying?
Yes. You can also think of it like this. The reactant anion is more stable than our product anion due to atom effects.
I gotcha. Okay, thank you.
Does that make sense? Perfect. So let's look at another example now, where we have an alkyne with a pKa of around 25 reacting with butyllithium. I'm going to draw butyllithium as the anionic form. So I'm going to attack the hydrogen and break my carbon-hydrogen bond. That generates the following anion. And as a byproduct, we get the following gaseous product, which quickly escapes our reaction mixture. So butyllithium is not only, or tert butyllithium is not only a strong base, but it also is favored via Le Chatelier's principle because it's a gaseous product, it quickly escapes the reaction. So just to note, this proton has a pK of around 48 to 50. So is this reaction reactant or product favored? Is this reaction reactant or product favored? What does everyone think?
Product.
Product favored. And that's exactly right, because we have a stronger acid on our reactant side and a stronger base on our reactant side and a more stable conjugate base on our product side. So this all points to a product favored reaction.
Can you just explain the first illustration you drew?
Yes.
Lost on that part.
So for acid-base reactions, our base abstracts a proton, and then we break our bond to our proton, in this case our carbon-hydrogen bond, to generate a new anion. So we've transferred our proton from our base to our acid, we transferred our proton from our acid to our base.
Where does the lithium go?
The lithium is just an associated cation. It just sits
Okay, because
around
that's
the
okay. Yeah, because that's what I was confused about was the
Yeah.
where the lithium went.
Yeah, so lithium is just an associated anion. Tert-butyllithium is commonly drawn like this, but it's not like there's an explicit carbon-lithium bond. You have an anion with an associated lithium cation.
Okay, that makes sense. Thank you.
If we have to draw reactions for the exam, will we need to include the ions that are dissociated in solution as well?
You can. I'm mainly looking for the direct reaction between the acid and the base. So I would recommend drawing tert-butyllithium and other alkyl lithiums as the anionic form.
Okay, got it. Thank you.
Mhm. Any other questions on this example? If not, let's keep going now. So in question 5, we're asked to rank the molecules in order of increasing boiling point. Okay? So, and we're going to note the major intermolecular forces found in each molecule. So our first order of business is to look at functional groups. So I see E and F have alcohols. Okay. While A and B have ethers. Now, why do I care so much about alcohols in this case? Why do I care so much that E and F have alcohols? What can alcohols engage in? What intermolecular force can alcohols engage in?
Hydrogen bonding.
Yep, exactly right. And does hydrogen bonding result in a high or low boiling point in general?
Higher.
Yep, exactly right. So comparing E and F, the next distinction we need to make, E would be a relatively linear alcohol. What would we call F? What do we call this structure in F? Is it linear or branched? Linear or branched?
Branched, right?
Yep, exactly right. And in general, which species have the higher boiling point? The linear or the branched species?
Branched.
For the higher boiling point?
Oh, linear.
Linear, yep. The linear species in general have the higher boiling point because for the branched species, they aren't able to pack on top of each other as efficiently. Does that make sense?
Yeah.
Perfect. The more regular the shape is of your molecule, the more efficiently it can pack, and in turn, the higher the boiling point. Okay, so A and B are ethers. So what what intermolecular force can ethers engage in? Anyone have a suggestion? What intermolecular force could ethers engage in? Does anyone have a suggestion? So ethers, what type of intermolecular force can these ethers engage in? Hydrogen bonding, dipole-dipole, London forces. What's the major intermolecular force for an ether?
Was it the dipole?
Yep, exactly right. These are polar molecules. So in turn, they'd engage in dipole-dipole interactions. Okay, now comparing A and B, B is a cyclic structure while A is a linear structure. Which structures have the larger boiling point? Cyclic or linear? Which structures have the higher boiling point? Cyclic or linear? Cyclic, exactly right. So then we have structure B is the next highest boiling, followed by structure A. Now looking at structure C and D, which are just linear alkanes, what's the major intermolecular force that those alkanes can engage in? What's the major intermolecular force? What was that? What was that? Sorry, I couldn't hear you there.
Is it London? Or
Exactly right. London, van der Waal, or dispersion forces. Yep. And comparing C and D, C is cyclic, D is linear, and in general, the cyclic compounds have the higher boiling point. So this is our complete arrangement and ranking of each of these compounds in order of increasing boiling point. Does this example make sense to everyone? Does this example make sense? Is everyone comfortable with the ideas presented in this example?
Yeah.
Okay, perfect. So let's keep going now and let's look at another example. So in this case, we're asked to draw an orbital diagram of the following molecule and indicate the hybridization of each atom and the orbitals used for each sigma and pi bond. And we're asked to assign formal charges to each atom. Okay, so I'm going to give myself some space for this one. Okay, so first at a preliminary glance, I'd see this nitrogen is sp2, this carbon's sp2, these carbons are sp, this carbon is sp2, and this oxygen has an sp2-like character. So with that established, I'm going to draw out, first I'm going to draw out my pi bonds. And I make sure to label the orbitals used for bonding in each case. And as we can see, we have a conjugated pi system connecting the majority of the atoms found in this molecule. Note that the 2p orbitals are used for bonding in this case. Okay, now that I've drawn out my first set of pi bonds, I'm now going to fill in my second set of pi bonds. And I'm using a different color for our triple bonding pi bond, because as we noticed, this pi bond is cross-conjugated. Does this picture make sense so far, where I drew out all of my pi bonds? Does this first picture make sense? Now I'm going to draw out my sigma bonds, and I'm going to try to respect as much as possible the length of each of the orbitals used for bonding. Note that this carbon in our methyl group is using its sp3 hybrid orbitals for bonding. It's not sp2 hybridized. The methyl carbon is sp3 hybridized. Okay, continuing on, drawing out our sigma bonds. One thing that we notice from this orbital picture, what orbital is this nitrogen lone pair located? What orbital is this nitrogen lone pair located? What
P
type of,
orbital?
what is it okay? Is it located in a p orbital?
Wait, 1, 2, 3.
So we're using our p orbital for bonding, right?
Yeah, it can delocalize, can it? So it's
Oh,
So then where is this lone pair located?
in an sp2.
Yep, exactly right. It's a localized lone pair. Does that make sense to everyone?
oh, yeah.
Perfect, perfect. Likewise, that's why one of these oxygen lone pairs is located in an sp2 orbital, while the other is delocalized. Continuing on, all we have to do now is just fill out our remaining sigma bonds. Just make sure that you're really careful in labeling your orbitals. So for example, the bond right here is a sigma bond between a carbon sp2 orbital and a carbon sp orbital. As you've noticed, that's why I draw my sigma bond between two of my carbon sp orbitals a little bit shorter than usual, because we're using shorter stubby orbitals, and we have as a result a closer overlap between our orbitals and a smaller distance between our bonded atoms. Does that make sense to everyone? Does that idea make sense?
Yes.
So now we've completely filled out our orbital diagram for this molecule, and we've labeled all of the orbitals used for bonding, and we've identified our conjugated p orbitals and our non-conjugated p orbitals. Does this example make sense to everyone? Does this example make sense?
Yep.
Any questions on this example that I can address? Any questions on this example that I can address?
I'm guessing you want us to try to draw this as neatly as possible for the test.
Yes, yes. So ideally it should be hand drawn.
Wait, so we can't submit chicken scratch?
For this one, it should at least be readable in terms of the orbitals used for bonding, and the orbital picture should be as clear as possible.
Oh,
Just
man.
like what we do in the notes. If it's completely blurry and I can't see anything, then it would be really rough for this type of question in particular. Any other questions on this example? Any other questions on this example? Okay, so let's keep going now. So this is an application of drawing resonance structures, and it's a type of problem-solving process that you actually apply in later chapters. So this initial paragraph talks a little bit about the SN1 reaction. It's used to substitute halides and other leaving groups with nucleophiles, such as an alcohol. This reaction proceeds through a carbocation intermediate, adding at the carbon containing the most stable carbocation. Those are words that I know. Consider the SN1 reaction for the following compound. A student carries out the reaction hoping to obtain alcohol 2. Instead, they observe alcohol number 4. So what's going on here? So starting from intermediate 1, this is what we've been tasked with. Reaction of intermediate 1 with water generates 3 unique products. Let's explain why 3 products are generated from this reaction and show how product 4 is generated. We need to draw resonance structures for cation 1 to justify our response. Okay, So starting from structure 1, so does everyone notice how our alcohol ends up at the position for our carbocation? Does everyone notice that for our first product?
Yeah.
Okay, so let's look at where our carbocation ends up in our other resonance structures. So let's just draw some resonance structures. So this is a resonance structure that I'm going to call pre-3. And as we notice, do we end up with our alcohol adding at that position? Do we see an alcohol adding to that carbocationic carbon?
Yeah. Or
Yep, it ends up at that exact position. Which makes sense because this reaction occurs at a carbocation, right? If we draw our final third resonance structure, lo and behold, we have a carbocation. Oops, one moment. Lo and behold, we have a carbocation right at the carbon needed to place our alcohol and to form product number 4. So as you can see, even though this problem looks relatively complicated, we can explain the regiochemistry. We can explain the products observed for this reaction by looking at the location of our carbocation in each of our contributing resonance structures. Does that make sense to everyone? So all I'm looking for you to do is to draw the resonance structures and then explain to me that, oh, we see an alcohol at each of our carbocation sites in each of these contributing resonance structures. So this is the carbocation that directly leads to product 4. Does this problem make sense to everyone? Any questions on this example?
There's no written response. The resonance structures explain it fully.
Yep. As long as you can, as long as you clearly show there's a carbocation at this position and we can attack that carbocation, this picture is more than enough to justify your response.
Got
And
it.
you can say we have 3 products because we have 3 carbocationic electron deficient carbons. And that in turn leads to 3 sites of reactivity, which in turn leads to 3 products. Does that make sense to everyone? For minor 3, all we have to do is we move our adjacent double bond over, and that generates a new double bond and a carbocation at our previously double bonded carbon. We'd follow this arrow pushing notation here. Does that make sense? So we're just shifting the double bond over to form a new double bond and a new cation. Perfect. Any other questions on this example? Okay, so let's keep going now, and let's provide a reasonable explanation for why alcohol 3 is a minor product. So if we look at alcohol number 3, what is the main difference between alcohol 3 and product number 2 and 4? What's the main difference? And really, let's focus in on our conjugated system. What is the main difference between alcohol number 3 and the other products? What's the main difference?
wasn't it because it was located at the cation?
that explains the regioselectivity. That explains which carbons get attacked. But looking at our products, looking at our final products, is there any difference in stability between these products? And really think about conjugation. Is there any difference in these structures in terms of conjugation and stabilization as a result of conjugation? What do we think? Let's look at these structures for a moment and let's consider which of these structures would be most stabilized via conjugation and which of these structures is least stabilized via conjugation. What does everyone think for this example?
I'm at a loss, I'm gonna be honest.
So thinking about it and comparing these structures, we notice that structure 2 and 3, we have conjugated alkenes, right? So in structures 2 and 4, we have conjugated alkenes. Correct?
Yep.
So then, because we have conjugated alkenes in structures 2 and 4, while in structure 3, our alkenes are not conjugated, which of these products would you expect to be the least stable product? Which of these structures would you expect to be least stabilized from conjugation? Structure 2, 3, or 4. Which structure does not have stabilization as a result of conjugation?
3.
3, exactly right. So then, looking at structure 3, what we notice is that structure 3 does not have conjugated alkenes, right? And as a result, structure 3 is higher in energy and less stable. So if there's any chance for reverse reaction, if there's any chance for a reversible reaction, we'll likely see very little of structure 3, as this structure is not particularly stable. It's not particularly favorable compared to our other two products. Does that explanation make sense?
Just to make sure, by conjugated alkenes, you mean that you can't push those bonds around or they become sort of localized, right?
Exactly. There's an sp3 atom that separates our two pi systems.
Gotcha.
So we can't delocalize our electrons across multiple atoms via resonance, and as a result, structure 3 is substantially less stable and it's higher in energy. And that in turn makes it less preferable to form comparatively compared to your other possible products, especially if this reaction is reversible. Does that idea make sense?
Yes, it does.
Perfect. So as you notice, even though it looks like a complicated example, are we still drawing from the same basic principles that we've used to explain the stability of simpler systems? Are we still drawing from the same fundamental principles of conjugation, resonance structures, stabilization via resonance, etc.? Are we still drawing on these same principles when we're solving this problem? Ultimately, we are, right? Perfect. Any questions on this example? Okay, let's keep going then. And in this question, we're asked, given the following formula and structure. So we're just going to focus on a small mismatch. We're just going to go from the following structure, and I'll give you the formula: 1, 2, 3, 4, 5. C5H 1, 2, 3, 4, 5, 6, 7, 8, 9. C5H9 NO2. Okay, so we see we have a DU of 2, so we can have 2 double bonds or rings. Okay. So with these rules in mind, let's see what the problem is asking us to do. We're asked to draw a structure with a stronger carbon-oxygen bond than the given structure that has no formal charges. Okay, so how can we get a stronger carbon-oxygen bond? How could we get a stronger carbon-oxygen bond? So if we want a stronger carbon-oxygen bond, what's one way that we could do that? Without having formal charges,
Or you mean like draw an isomer?
Yep, exactly.
And is it okay, rather than using DU, if we use the degrees of saturation?
Yep, that's more than okay. And let's change this example to carbon nitrogen. As I noticed that the question that I provided originally, I would have a different structure here. Let's try to draw a structure with a stronger carbon nitrogen bond than the given structure. So what's one way you can get a stronger carbon nitrogen bond? How do we get a stronger carbon nitrogen bond? So currently we have a carbon nitrogen single bond. So how do we get a stronger carbon nitrogen bond? What should we do then?
Could you make it a double bond, or is a lone pair localized?
Yeah. No, we can draw a constitutional isomer that has a double bond. Sure. So when we are asked to draw a structure, we are asked to draw any constitutional isomer with the same formula, but with a different connectivity of atoms.
Oh, right. Okay.
So in this case, we can take this structure and just shift our double bond around and draw a something like this, where we have a carbon-nitrogen double bond. In this case, we'd have a stronger carbon-nitrogen double bond, and we'd still have no formal charges. Does that first example make sense to everyone? Does that first example make sense?
Yep.
Perfect. So let's keep going now. We're asked to draw a structure that has a proton with a pK of around 26. So what proton has a pK of around 26, 25 or 26? What are we looking for here? What functional group? What has a pK of around 26? What are we looking for here? pK of around 26, what ketone containing functional group does that match? An amide, an ester, a ketone, an aldehyde. What structure? What functional group does that match? What structure has a pKa of around 26?
And ester?
An ester, yeah, that's one option. Is there another functional group that has a pKa of around 26?
Do aldehydes?
Aldehydes are closer to 20 to 22. I was thinking more of an alkyne. So both options would be valid, right?
Those are both 25.
Yep. Which is pretty close in terms of the ballpark range. So then, let's draw the structure with the alkyne, since that's a little bit more interesting. So we'll draw our alkyne. Okay. So we have 5 carbons to work with. Okay, and we can't have any additional rings. We can't have any additional rings. So let's just keep going from here. We have our alkyne. We've used up 3 carbons. We have 5 that we can use. Oops, can't do that. 1, 2, 3, 4.
Couldn't you also use a nitrile?
Nitrile is closer to 30. It's not unreasonable, but it wouldn't be as preferable. You can do a structure like this. There are hundreds of possible options. To showcase the ester, for those who are curious, the ester could be something like this. 1, 2, 3, 4.
On the pKa table, it says a nitrile is 25 as well.
Oh, okay. Then that would be fine. Nitriles are typically a little bit less acidic than an ester, but a nitrile is also perfectly fine to include. We can draw a structure with a nitrile as well. So because we used a triple bond, again, 1, 2, we're somewhat limited.
Oh, I see. Oh, I see the issue.
No, but it's still fine. It's still more than okay. It's still more than okay. You just have to,
We'll really play with it.
yeah. But that's more than okay. Let's not draw something let's not draw a structure that's potentially explosive or anything like that. Let's see. 1,
How's
2,
that though?
3, 4. What was that?
No, I was just saying that's where the fun's at.
Yeah, that peroxide would probably not be very stable. You make that as a byproduct if you're doing like alpha oxidation, but you typically reduce it down in solution. Let's see. So we have 1, 2, 3, 4, 5 carbons. Let's check as well for our nitrile. Everything looks good on that side. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. Yep. So as you see, we can draw a range of possible structures that would satisfy this solution. Does that make sense to everyone?
Yeah.
Perfect. We can draw a structure containing an aldehyde functional group. Well, that's easy. We already have one. And there are a range of possible solutions to this. Again, as long as you have this aldehyde functional group, you're more than good to go. Does this make sense to everyone? So this is simultaneously a test of drawing constitutional isomers and making sure students are familiar with common pKa values as well as common structural functional groups.
Yep.
Perfect. So let's keep going now. We're next asked to draw a structure that is more Lewis basic than the drawn structure. So let's take this drawn structure here. Okay, so we have this relatively basic amine. What would be a way to increase the Lewis basicity? What would be a way, so thinking about Lewis basicity, so Lewis basicity concerns lone pair donors. So what is a way for us to maximize the number of lone pair donors present in our molecule? What's one way of doing that? So for example, this amine group, this alcohol functionality, this ketone functionality are Lewis basic functionalities. What's one way that we can maximize the number of Lewis basic functional groups? Well, we can just generate and draw a structure with more of these Lewis basic functional groups. So something like this would be perfectly reasonable to draw, where we have more lone pair donors available for coordination and reaction with Lewis acids. As long as you don't start getting rid of lone pair donors, you'd be more than okay for this problem. Does this make sense to everyone so far? Does this example make sense?
So kind of making sure the lone pair donors are more outside of the main structure, kind of, in a way, right?
Or we have more lone pair donors that can effectively participate as Lewis bases. So the ketone is less Lewis basic than an amine or an alcohol, for example.
Okay.
Mm-hmm. And ensuring that the electron density is most localized on each of our lone pair donors as possible. So we want to minimize conjugation of our lone pairs and delocalization of our lone pairs via resonance. Does that make sense?
You mean, so basically we want the most localized structure we can get.
The most localized lone pairs as possible. Yep.
Okay.
Perfect. Okay, and next we're asked to draw a structure with a higher boiling point. So given our original structure, looks something like this. What's one way that we can maximize boiling point? What are some ways that we can maximize boiling point? What are some factors that maximize boiling point? If we want higher boiling points,
Functional groups, and if it's like
Yep.
silic.
Yep, and what was that?
And if it's silic.
Cyclic, yep, exactly.
Sorry, cyclic, yeah.
Cyclic structure. And what intermolecular force results in very high boiling points?
Hydrogen bonding.
Hydrogen bonding, exactly right. So let's make a cyclic structure with a ton of hydrogen bonding, and lo and behold, the structure that we previously drawn seems like a pretty
Can't you
good
just choose the same one?
Yep. If it fits, it's more than okay. this structure would be substantially higher boiling. Another possibility would be to do, for example, a cyclic structure with like a carboxylic acid, which can participate in pretty strong hydrogen bonding. So for example, this structure would also be acceptable. Does that make sense? Do these problem sets make sense to everyone in terms of how the questions are supposed to be answered and in terms of the thought process that we're supposed to use? The actual exam you get will be way easier. The questions on some of the practice exams are a little more difficult than the exam, just so that way it's fair preparation. Let's look at a challenge question. In this case, cis and trans isomers can have drastic differences in boiling point, physical properties, and pKa. Our job is to provide a reasonable explanation for why compound A is way more acidic than compound B. So let's draw the conjugate bases. Let's draw the conjugate bases and let's see if someone can catch the gimmick for this question. The extra credit questions are a little more difficult than usual, but I find that they can be solved with a one-sentence explanation. So, would someone like to tell me why is structure A more acidic? Why is structure A more acidic? Would someone like to tell me? Someone like to have an idea for this?
The atom effects, like dipoles, maybe?
Well, they both have the same relative dipoles, you know, they're both sort of going about in the same.
Right.
This electron density is delocalized via resonance. What else can stabilize a lone pair? What interaction can also stabilize atoms? So just to jog your memory, when we have like an anion in solution, what is the solvent doing? What does the solvent do to stabilize our anion? What can stabilize a conjugate base? What can stabilize a conjugate base? What can stabilize a conjugate base? What do we call this interaction with the solvent? What do we call that interaction? What intermolecular force is that? Hydrogen bonding, okay? Now, which of these structures can engage in hydrogen bonding? Which of these structures has the correct geometry for hydrogen bonding to occur? Which of these structures has the correct geometry for hydrogen bonding to occur? Which of these structures has the hydrogen and lone pair close together? Structure A or structure B?
Structure A.
Exactly right. So structure A.
Oh, so it just bonds to itself?
Yep, it can engage in hydrogen bonding in an intramolecular sense. So structure A, the conjugate base is stabilized via intramolecular hydrogen bonding. And that in turn, because our conjugate base is stabilized, structure A is more acidic. Does that make sense? It's the exact same way that solvent stabilizes conjugate bases. So even though it looks pretty tricky, if you draw the structure and you just compare the cis and trans isomer, you'll notice that only one of these structures can actually engage in that intramolecular hydrogen bonding. Does that make sense to everyone? So then to finish off, would you expect acetic acid to be more or less acidic? So clearly, if we know the pKa is around 4.76, then it's clearly less acidic than either of these compounds. And the reason for that is that compound A and B are heavily stabilized via conjugation and delocalization of the, so conjugate bases of compound A and B are heavily stabilized via conjugation and delocalization of the anionic lone pair. And because we're able to delocalize our electron density over multiple atoms, we're able to stabilize our electron density, and in turn, that's why compounds A and B are more acidic than acetic acid. It's delocalization and stabilization of our conjugate base via resonance delocalization. Does that make sense to everyone? Does this make sense to everyone so far?
Yeah.
So that's about it for the, let's look at one more. Would you expect compound C to be a more or less acidic analog of compound A? So if we look at compound C and we look at the conjugate base of compound C, does anyone notice a bit of a problem in compound C? Does anyone notice a bit of a problem? Looking at the conjugate base of compound C, would you expect this conjugate base to be more or less stable compared to the conjugate base of compound A? And this really requires us to think a little bit about what do we need for a hydrogen bond? Does anyone notice the difference between these two compounds?
There's one less site for hydrogen bonding.
Can compound C hydrogen bond with itself? No, compound C cannot. So you're exactly on the right track there. There's one less site for hydrogen bonding, and as a result, the conjugate base of compound C cannot hydrogen bond with itself. We've gotten rid of that other hydrogen, and as a result, compound C would be less acidic because the conjugate base is less stable. Does that argument make sense to everyone?
Yeah.
Perfect. So that's about the end of our practice exam. There's another practice exam posted on Canvas if you'd like to engage in additional practice. Is everyone comfortable with these examples? Is everyone feeling a little bit more confident after we went over a practice exam together as a group? And
Yeah, honestly, this I'm very happy I came back to actually review.
that's good. That's good. Do the questions make a lot more sense now in terms of the concepts and how the concepts are applied?
Yeah.
Perfect. And does everyone notice how a lot of these questions are pretty similar to the homework as well? The homework is multiple attempts, so if you want to refresh any of your pKa values, if you want to refresh accounting for resonance effects, etc., all of those practice examples are still available for you to review the questions for, and that would be good practice in preparation for the exam. Any other last minute questions before we close out this session? I'm glad that this was helpful to everyone. I know a lot of these problems, it may take a moment to figure out, well, how is this connected to what we've learned? But a lot of these examples are designed to build the skills that you'll be utilizing in later portions of this class. So,
And then where can we, are we going to be able to locate this recording so that we can review it again?
Yes, it's available via ConferZoom, and once it's processed, I'll also post it, hopefully by tomorrow, once the closed captions are in, and I'll post it in Canvas.
Okay, cool.
Mhm. Any other questions that I can address? In terms of examples, don't worry about example C. Example C is not at the level of difficulty that you'll see on the exam. Example C is a little tricky. All the other examples that we covered are perfectly fair game and could just as easily show up on the exam. Could you explain conjugation one more time? Yes, so let's look at an example where it most comes up. So let's suppose we're looking at this amine, for example, versus an allylic amine. Now, essentially, the hybridization depends on how the hybridization is dependent on conjugation, in that if a nitrogen has a lone pair adjacent to a pi system, so we have our pi bond adjacent to our nitrogen lone pair, the nitrogen will prefer to adopt an sp2 hybridization so that the lone pair can be placed in a p orbital and be conjugated with the adjacent pi system. So in conjugation, what we are doing is we are delocalizing our electron density over all atoms participating in the pi system. So we have delocalized our electron density.
And that's why the hybridization ends up changing.
Yes, because we're able to stabilize our lone pair and stabilize our molecule and get a lower energy system if our lone pair is present in a p orbital and able to participate in conjugation. Does that make sense?
Yeah.
Otherwise, the nitrogen will be sp3 because there is no inherent benefit to adopting a planar conformation. So geometry depends on the adjacent atoms and depends on conjugation and resonance effects. You can also think of it as if there's a minor resonance structure where we have an sp2-like nitrogen, such as that shown here. Now, of course, this is a minor resonance structure, but it influences the geometry and the preferred geometry for our nitrogen atom. Does that make sense? Perfect. Any other questions I can address before we close out today's session?
Not for me, so I guess have a good night, Professor.
Yes, and I'll see everyone in lecture on Thursday. The review session for tomorrow will be for my other class, which is 107. But on Thursday, I have office hours. And of course, you can always ask me questions if you're working through the other practice exam. And I'd be happy to answer your questions during office hours or via email. Perfect. So I'll close out today's recording. Enjoy the rest of your evening.